Okay, in case you're wondering why this title is different from the announced title, is because there was a little bit of confusion with mailing the talk. And I had given this talk on April 21st at the Rensselaer Polytechnic Institute, and the small variation of it that I prepared for here somehow got lost between New York City and Rome. So last night we loaded this other talk, and it's essentially the same, so don't worry about it. It's because I was giving the talk to a medical imaging group. I had medical imaging in the title. But in a way that's a good thing, because if anything that I would like you to take away from this talk is that superiorization is a very general tool. It's applicable in many, many different fields for many, many different things. And I hope to convince you that it's a good thing. Let's see. Yeah. Yes. So superiorization is a way of doing constraint optimization. A novel, different way from what has been done traditionally. But I want to convince those of you who are not already convinced that constraint optimization is a very important topic. And thereby implication, superiorization, which helps you to do that kind of thing, is also important. There are many, many, many applications that use constraint optimization. There's no end of them. But usually what happens is that you have a physical, engineering, medical, whatever field, and or even in computer science, mathematical logic. They have a bunch of constraints that you want to satisfy, all kinds of things. So you have constraints which arise from the desire to produce a solution that is constraint compatible. And the constraints could come from physical measurements, from prior considerations, from knowing that certain things are impossible. So the constraints are physically or otherwise obtained. Now, as was mentioned, computerized tomography is my own particular research field. There the constraints arise from detector readings from the instrument. So the images that you want to produce have to be somewhat compatible with the measurements that you have made with the computerized tomography scanner. Now, constraint compatibility, as I've defined here, is a somewhat vague concept. Note that I talk about compatibility, not exact satisfaction of the constraints, because typically exact satisfaction is not the thing you want to do. In computed tomography, usually your measurements are inconsistent, and there is no image which exactly satisfies all the constraints. So you want to be compatible with it, not necessarily exactly satisfying with it. And then once you relax of what you accept as constraint compatibility, uniqueness goes out through the window, and there may be many things that you will say, these are constraints compatible, these are good enough from the point of view of being consistent with the constraints, because you know, for example, what kind of errors you have in the data collection. So when this happens, then, and this is the idea of constraint optimization, in such cases, usually what people do, that in addition to the constraints, you introduce an optimization criterion. to distinguish between better constraint-compatible solutions. And for example, in medical imaging, the human body is made out of organs, so it's more or less piecewise homogeneous. And you can express that by a mathematical formula, the level of piecewise homogeneousness, and you want to find a constraint-compatible solution which is also satisfying the requirement that the image is piecewise homogeneous. And superiorization is a recently developed heuristic for constraint optimization. Note the heuristic, it will come out clearer later. I just want to say that heuristic approaches have been found useful in many applications of optimization, mainly because they are often computationally much less expensive than the exact counterparts, but nevertheless provide solutions that are appropriate for the application. The basic difference between a heuristic method and an exact method, which is usually what mathematical-minded optimization folks do, is that the exact methods converge in the limit to something that can be mathematically specified. We're not going to do that. You will see what we're doing. Okay. So this is the idea of superiorization. First of all, it is the case that in many applications, there exist efficient iterative algorithms for producing a constraint-compatible solution without the optimization criteria. If you just want constraint compatibility, they are usually around algorithms which work extremely efficiently and get you one. Problem is, what it gets you to may not be very desirable. That is why we need the optimization criteria. Now, many of these algorithms have the property of being perturbation resilient, which means that even if certain kinds of changes are made at the end of each iterative step, the algorithm still produces a constraint-compatible solution. So the idea here is an algorithm, iterative, it produces a sequence of images, and you know that it converges to something or gets to something which is constraint-compatible. And if the algorithm is perturbation resilient, if you can do the following, then after every step you make a little change to the image that you got at the end of the step, then you do the next iterative step and you make another little change and so on. And under certain circumstances you can prove that it still converges to a constraint-compatible solution even though you messed around with it as you iterated. This is the property which is exploited in superiorization by using such perturbations to steer the algorithm to an output that is as constraint compatible as the output of the original algorithm, but it is superior to it according to the given optimization criteria. And what is the most wonderful thing about this is that there is a totally automatic procedure that turns the iterative algorithm into a superiorization. Typically, it is easy, relatively speaking, to produce an algorithm which leads to constraint compatibility, but much more difficult to produce an algorithm that optimizes, not just compatible with the constraint, but also optimal by according to some other criterion. That is usually a much more difficult problem. Look up books on constraint optimization, here thick, full of methods. And what superiorization does for you is gives you an automatic procedure that once you have the original algorithm for constraint compatibility, it produces an algorithm which is a superior version, and it produces better images according to the optimization criteria. And this is a great thing for somebody like myself, who works with lots of different optimization criteria, because instead of having to each time to do 5 years of work on mathematical research to prove that my optimization algorithm works, I just feed this into the system. Can you read this? I just feed this into the system, and out comes the superior algorithm. Yeah, the darker you can make it, the better. It's, No, I don't need a keyboard. It's, no, I'm worried about people
not so
reading
bad,
that.
it can be read.
You can read it, okay. I spent 12 years working in I spent 12 years working in radiology department. The radiologists sit in very dark rooms to discuss the images for good reason. Okay. Now, what is the essential difference between constraint optimization that has been practiced throughout the years and superiorization? There's a different view of the world. Later on, I will have lots of slides full of mathematics. I will essentially not discuss them. Just show you that I'm a respectable mathematician and I have formulas. But in an hour, I don't have time to explain all that. But I want to sort of get across the basic idea. Both in superiorization and in classical constraint optimization, we assume that there is a domain, call it omega, and an optimization criterion that is specified by a function phi that maps omega into the real numbers. The larger the values, the worse the image is. So phi, a low value of phi indicates that's a good image. An example which I will say a little bit more later on, one of the things that people have been doing lately quite a bit with image processing is use total variation to measure how good the image is, and the smaller the total variation of the image, the better the image is considered because of all kinds of things that I will not get into. Now comes the problem with classical optimization. In classical optimization, it is assumed that there is a constraint set C, and the task is to find an element x in C for which phi x is minimum. That is the classical formulation of constraint optimization. Constraint set C, find an x in C for which the function that you're optimizing assumes the minimum value. Now, in practice, there are problems with this. Quite typically, in just about any applications except the ones which come from purely mathematical considerations, the constraints may not be consistent. So C could be empty, and this optimization task, as stated, doesn't make any sense at all. The second problem is that the iterative methods of classical constraint optimization typically converge to a solution only in the limit. Lots of beautiful mathematics proved that if you run this algorithm forever and ever and ever, you will get nearer and nearer to the minimum, but you never get there. Now in practice, you have to stop. And wherever you stop in practice, the chances are that at that moment you're not in C, because the mathematical theorem only says that if you run it forever, you will get to an image which is in C and which is optimal according to phi in C. But when you stop in practice, you may not be in C, and if you happen to be in C by some luck, the chances that that will be the actual minimizer is just about non-existent. Now, in superiorization, we handle these problems by giving up the wonderful mathematical aim of converging in the limit to the ideal. We replace the constraint set by a non-negative real-valued function PR, where PR stands for proximity, that serves as an indicator of how incompatible x in omega is with the constraint. So instead of saying, I want to satisfy all the constraints, I say I introduce a function which for any image x tells me how badly I'm violating the constraints with that image. So you would like, in intuitive thinking, you would like the value of PR to be small for whatever you propose as a solution. And the merit of an actual output of the algorithm is then given by the smallest of two numbers, PRX and phi-x. And roughly, if an iterative algorithm produces an output X, then its superiorized version will produce an output X prime for which the proximity is not larger than the proximity to the output of the original algorithm, but in general, the value of phi is much smaller. That is the nature of superiorization. So we don't lose constraint compatibility, but we improve goodness according to the optimization criteria. Well, now begins to have lots of mathematics, which I promise that I will impress you by, but I'm not going to cover in detail, but just as we go along, I want to give you some indication of the kind of specific things that can happen. For example, the set omega. The set omega would be typically a subset of some vector space, a real vector space, J-dimensional vector space. And one possible way of defining omega, that only those images are in omega which are non-negative and where the value at every pixel is less than or equal to 1. This could be 1 omega. The set of all images where the grayness is between 0 and 1 in each pixel. If you're in computerized tomography and your interpretation of x of j, that it's an estimate of the X-ray linear attenuation coefficient in the pixel, then this constraint would be satisfied for any human body. In an application, you usually have a problem set. And in CT, the problem set would be the set of specific things that you have to reconstruct. So the problems in the problem set would be specified by a pair, A, where A is the system matrix of the instrument that you're using, and B, where B is the measurement vector provided by that instrument. So what you are looking for is algorithms which, for any system matrix and any measurement vector, will give you some constraint compatible element in omega. Then what you need, remember I have said that constraint compatibility is not defined by a proximity function. So for the problem T, this particular problem, for this particular problem T here, the proximity function, one of the things you could do is you could take the norm of the difference between applying A to your proposed solution and subtract that from the measurements. If your proposed solution is nothing like what you've been measuring, then this difference would be large. The norm of this difference would be large, and presumably those images for which the norm of this difference is small are at least compatible with the constraint provided by this particular problem. And we'll get to that definition. Then we need the notion of an algorithm. In this context, the algorithm for a problem structure which consists of a problem set and the proximity function on the problem set is defined by an operator. And this operator will produce things from vectors, it will produce new vectors. So PRT, the algorithm for T, the algorithm is such that for each problem there's a specific version of it. We'll map delta, which is a superset of omega, into omega, which means it maps omega into omega. And so if you start with an x in omega, then, and you keep applying this iterative step of the algorithm, you get an infinite sequence of images. So you start with x, which is your initial image, and you keep applying the algorithmic step to x, infinite number of times, and that gives you a sequence of images. An example for the city problem, where the problem is specified by a system matrix A and the measurement vector B, is provided by the following iterative method. It's called ART. And ART is defined here. This is the iterative step of ART. You have x, and then after the iterative step, you have pt of x. And you get there by a sequence of sub-steps, u1 up to uiq, where ui has to do with the ith equation in this system of equations. Right, it's a system of matrix, so it's a measurement vector. So each row provides you with an equation, aix equals bi. And what you do is you kind of try to satisfy this individual equations one by one, the first one, second one, until the last one. And what this formula says how to do that. And then when you're done, you may not have the result in the omega, in the domain. So Q brings it into the domain. It sets every value less than 0 to 0, every value greater than 1 to 1. And therefore, once you apply Q, then you have a vector in omega. And so this is indeed something which if you start in omega, and you keep applying, you stay in omega. Okay, so what is the output of a superiorization algorithm? Because I haven't talked about that output. I talked about that it produces an infinite sequence. So the way we think about it is that the output associated with a problem T and an infinite sequence R and a user-selected epsilon, where epsilon is a positive number, is the following. R is an infinite sequence. It could be the infinite sequence that is produced by the iterative method for the problem T. What you do is you look at the infinite sequence, and after each step you check whether the proximity for the particular problem T that you're trying to solve is less than epsilon, or less than or equal to epsilon. And the first time you hit a vector for its proximity is less than or equal to epsilon, you call that the epsilon output. So for given an epsilon, you get an output, maybe. Because of course it could happen that you get an infinite sequence where you never get below epsilon. That means that your algorithm is not good if your desire is to have epsilon compatibility, and you better design a better algorithm, or be less ambitious on how compatible you want the answer to be. Clearly, if there is such an X, then it is unique, because it's the first one in the sequence that you hit. And if there is no such X, then we say that the output is undefined. Now, strong perturbation resilience is a technical definition. I cannot really go into details, but let me sort of point at things which will give you the idea. In the original algorithm, what we do is that we start at some initial vector in omega, and we keep applying the operator, and the output is the first time we get below epsilon. In a perturbed version, what we're going to do is that we don't apply the algorithmic operator to the image xk, but we apply it to xk perturbed by something. And there's some limitation of how much perturbation you can do. Obviously, you cannot do any mathematics. If in each iterative step you can perturb it anywhere, then you can just keep throwing it back to the same point at the end of each step. But the restrictions are that these vectors, which is the direction of the perturbation, form a bonded sequence, and these scalars by which you weight the vectors, Vk is the perturbation direction for the k step, beta k indicates the size of the perturbation, and you want the beta k to be a convergent sequence. That is, the sum of all the beta k must be less than infinity. And a strongly perturbation resilient algorithm is one where if you apply such perturbations, you are guaranteed to get to a result which is as epsilon compatible as the unperturbed algorithm. Now, this is a rather abstract definition, but it so happens is that there is a mathematical theorem which guarantees strong perturbation resilience based on much simpler classical mathematical concepts. And here's the theorem. If P is an algorithm or program structure such that the algorithm is all bondedly convergent, the proximity function is uniformly continuous, and the algorithmic step is non-expensive. These are all very simple standard concepts associated with iterative methods. Then P is strongly perturbation resilient. So in order to prove this rather funny looking definition on my previous slide, what we have to prove this is three fairly simple mathematical conditions, which here is an example that the ARC algorithm for certain sets is strongly perturbation resilient because you can easily prove every one of these things over here. So even though it looked like that I introduced a notion that may be an empty one, and if you go back here, there's a perfectly fine mathematical definition, but just by looking at this, it's probably not clear to you that there are any strongly perturbation resilient algorithms at all. Is there any algorithm that satisfies this definition? The theorem says yes. In fact, there are many algorithms which satisfy simpler conditions satisfy this. The final new concept has to do with the selection of the direction into which, and in fact, that comes out of the non-ascending nature of the vector that I use here. If you look at the definition of what a non-ascending vector is, it guarantees that you cannot be stuck in the while loop. Most important, otherwise this would be just an algorithm which would just be going round and round and round in this while. So you jump out of the while loop. You certainly will jump out of this while loop because at the end of each of the other one, you increase n by 1, so you eventually get here. So this is an honest-to-goodness algorithm that produces an infinite sequence. And note, it's totally automatic. If I have an algorithm for P, I just copied that algorithm in here, and the rest of it is just bookkeeping, so to speak. I mean, we know how to produce an ascending vector. These things are the same. So the superiorized version of one algorithm looks very similar to the superiorized version of another algorithm. The differences are that where you do the algorithmic step and where you make use of the optimization criteria. But it's quite automatic. You don't have to think about it. There's nothing wrong with thinking, but sometimes it has happened in practice that it took 5 years after the appearance of an algorithm which produced a constraint-compatible solution before somebody could produce an algorithm which gave its optimized version using classical constraint optimization. Now, you just plug it in and you get it. So, to say it again, the above description produces automatically the superiorized version of any algorithm P. Because of what we do, it will produce a smaller value of phi, and so it can save a lot of time of researchers when the application of interest gives rise to a new constraint optimization problem. And another thing that can happen is that the superiorized version may actually be computationally superior as well as from the point of view of producing a better value of phi, because some of the classical optimization algorithms involve huge matrices. So we had the A matrix in the example I gave you, but say quite typically when you want to do constraint optimize something, even though the A is a sparse matrix, you actually work with something like A transpose A, a square matrix, and that is not sparse. And the computation involved in that may be beyond even quite powerful computers. I mean, I work with big problems in medicine, and there are really large computers which cannot handle some problems which naturally arise, for example, in radiation therapy planning. And in the superiorized version, you don't have that problem. You only use the original algorithm. If the computer is big enough for the constraint-compatible solution, the superiorized version will not defeat the requirements of the computer. And the other thing that can happen that actually the results will be faster. Let me give you an example of this. This is a paper which we recently published with Yair Senzo, Ron Daviti, Reinhard Schulte, and a postdoc of Yair. And in this we compared a standard algorithm referred to as PSM of constraint optimization, which was the topic of this author's doctoral dissertation. So we had an expert on that algorithm, what we were doing, we were using for the function phi the total variation, which I mentioned before. And here is the definition for any image x. The total variation of x is a digital approximation of the integral of the magnitude of the gradient over the image, and you calculate it by adding together over all pixels except the one in the lost row and the lost column, the difference between the pixel value and the pixel to the right of it squared, the difference between the pixel value of the pixel and the pixel below is squared. You take the square root and you sum this over all pixels. That's the digital total variation, and this is used, as I said, you look it up. In the image processing literature lately, total variation minimization is a very, very often occurring possibility. We tested it out on a Phantom which had 235,225 pixels, and it was a representation of the human head. And we calculated the data, the B in the AXAB situation, by estimating line integrals of the Phantom for 18,524 lines. And we first applied the classical method and the superiorization, and we obtained the following results. This on the left is the Phantom, mathematically described cross-section of the human head with lots of tumors in it. The thing in the middle is what is obtained by PSM, and the thing on the right is what is obtained by superiorization. We stopped the PSM at iteration number 815 according to criteria that have been proposed in books as to when you should stop PSM. And that time the proximity value of the proximity function was 0.0422. And this required 2,217 seconds of computer time on the computer that we used. And the TV value at that time was 919, which is good because it's better than the TV value of the Phantom. We are trying to minimize TV, so we should be able to beat the TV of the Phantom. Then we use the superiorized version of ART, and we have chosen for epsilon this very number, the 0.0422. That will guarantee that when we stop with the superiorized version of ART, the proximity will not be worse than with PSM, because that we stop it when we get below to the proximity of PSM, and that produced the output on the right, and the computer time required for this was only 102 seconds, over 20 times faster than the classical method. And furthermore, the TV that it produced was actually smaller, 876, as opposed to 919. So we could do something 20 times faster, which according to the criteria that we try to achieve is better. And other applications where we try this out is positron emission tomography. In positron emission tomography, you're counting number of photons that were generated with a number of lines, and because the underlying model physically is a Poisson distribution, the appropriate proximity function is the so-called Kullback-Leibler distance, which is defined over here. In the city application, we take the known difference between AX and B. Here we have another distance, which is used quite a bit in statistics when Poisson distributions involved. There's a perfectly fine definition, and trying to minimize this is a respectable endeavor in positron emission tomography. And in fact, here is a classical algorithm. This is called the expectation maximization algorithm, special case for this function. And this is the iterative step of it, right? It's perfectly well defined, and it's been proved quite a few years ago that if you run this algorithmic step forever and ever, you will converge to a minimizer of the Kuhlbach-Leiber distance. But of course in practice you don't run it forever. And in fact what happened in practice, that having proved this beautiful mathematical theorem that this algorithm converges to a minimizer of the Kuhlbach-Leiber distance, people started applying it and found that as you use the algorithm, originally you get images which look better in the sense of you could see medically what you want to see better, but after a while the images deteriorate. The images get very noisy looking, salt and pepper noise, and what happens that in positron emission tomography, the measurements are quite unreliable because the number of photons is rather limited, and as you keep iterating, you are fitting the noise in the data rather than the important information. So people have designed algorithms where instead of just trying to minimize the Kuhlbach-Leiber distance, they took into consideration also something which measures how much local noise you have. And here the definition of phi is the sum over all interior pixels of the value in the pixel minus the average value of the 8 neighbors. And for a smooth image this should be 0. An absolutely smooth image it should be 0. For an image which varies a lot locally, this gets worse. So this is a measure of how smooth the image is locally. And let me get rid of that. Here is an illustration of a reconstruction of activity in the brain. Now this looks quite different from the previous phantom. In the previous phantom it was showing the X-ray attenuation in the human head. Here is showing the accumulated radioisotope in the human head. Those are entirely two different physical quantities. So the phantoms look different. And this is what we got if we use the EM algorithm without superiorization, and this is what we get if we use the EM algorithm with superiorization. And to see better where the differences are, I plotted the values along the 323rd column, which is approximately here. And the red is the values in the phantom, which I'm not showing. The green is the values in the reconstruction without superiorization, and you see the large local variations. And the blue is the reconstruction with superiorization, where these local variations are much reduced, as they ought to be, because we are superiorizing to make the value of that phi smaller. Now, the other nice aspect of this that I'm talking about is that parallel implementation is quite possible. And just to indicate to you why this is important is that I wrote a book which appeared in 2009 on image reconstruction, and in it I have an illustration of reconstructing the beating heart from computed tomography projections. And I used a piece of software called JSNARC on a single sequential processor, and the reconstruction that I report on in the 2009 book took 3 days to produce on my single processor, not particularly powerful one. But clearly, such times are totally useless in a clinical environment. I mean, if somebody is having a problem with his heart, you cannot wait 3 days to get the output. So we've been looking into using modern computing equipment to make this more medically reasonable. So in particular, I've been working with, I already mentioned Reinhard Schulte was one of the authors of that paper comparing superiorization PSM. Reinhard Schulte is a radiation therapy expert, and in particular he uses proton therapy. And for that purpose, in order to be able to do proton therapy, you really ought to do proton computerized tomography, so that what you're using in the therapy plan physically matches what you reconstructed. And what we have found that a parallel implementation of the superiorization algorithm using a 96 message passing interface processors succeed in reconstructing the 3D distribution from over 2 billion measurements, 2 billion, in less than 10 minutes. Now that gets to be reasonable, because the patient for whom you're collecting data, it takes at least 10 minutes just to set up the patient and take the patient out of the scanner. The actual collecting the data is very quick. It's seconds, but you know, you have to have the patient lie in the machine, align the machine, so on and so forth. So 10 minutes is, for this application, is real time. I call real time for an algorithm if the algorithm doesn't slow down the overall process. So if it takes 10 minutes to collect the data and you can reconstruct in 10 minutes from the data, you're in good shape, in my opinion. And this number, the 3 billion, is 40 times the number of measurements for the reconstruction of the beating heart that I've reported in my books 5 years ago. And yet the reconstruction time is 400 times faster. So really, for not particularly, I mean, these message passing interfaces, these are nothing exotic nowadays. You can buy them for not terribly large amounts of money, and you can achieve this kind of enormous speed ups compared with what I was able to do for my book 5 years ago. Now, to say a little bit about algorithms, what makes this happen? Remember when I was describing the ARC algorithm, I said that one iterative step of ARC consists of looking at one measurement, another measurement, another measurement, and doing something for each one of the measurements. Now, that description sounds like inherently sequential, not parallel. You have to do this step, and this step, and this step, right? But if you have that one measurement is for this ray going through the head, and another measurement is for this ray going through the head, and those two rays do not do not intersect, then applying the steps one after the other results in an update which is like this, because the change you made at the end of the first step doesn't influence what you do in the second step, because the rays don't intersect. And so you can describe this whole thing as X plus, this whole thing is parallel now, not sequentially. And so if you break up your huge data set of billions and billions of measurements in such a way that in any subset, for any two measurements, the inner product of the rows of the system matrix is 0, then you can automatically parallelize it according to this formula. So you can see that by understanding the problem and understanding the mathematics of the algorithm, suggests ways of parallelizing which allows you to do this enormous speed up that I mentioned before. Okay, well that's just about it. To summarize, many applications use constraint optimization with the constraints arising from the desire to produce a solution that is constraint compatible. It is typically the case that a large number of solutions could be considered good enough from the point of view of being constraints compatible, and in such a case an optimization criterion is introduced that helps us to distinguish the better constraint compatible solutions. The superiorization methodology is a recently developed heuristic approach to constraint optimization. The underlying idea is that in many applications there exist computational efficient iterative algorithms that produce constraint compatible solutions. Often the algorithm is perturbation resilient in the sense that even if certain kinds of changes are made at the end of each iterative step, the algorithm still produces a constraint compatible solution. This property is exploited by using such perturbations to steer the algorithm to a solution that is not only constraint compatible, but is also desirable according to a specified optimization criteria. The approach is very general. It is applicable to many iterative procedures and optimization criteria. And most importantly, superiorization is a totally automatic procedure that turns an iterative algorithm into superiorized version. And I believe that is the end. Thank you.
Thank you very much for this nice and interesting lecture. So we have now time for questions, remarks. Are there some questions?
Make a question. You have formulated in one of the slides your problem with big O T epsilon sequence. In one of the slides you formulated big O T was the process, epsilon the stop, and then a sequence.
Yes, okay. This, you're talking about it?
Yes.
Okay, good.
Now, in the following slides, okay, looking at this, I was expecting that you will stop the process, you stop the algorithm using epsilon.
Yes.
But later, when you showed your algorithm, I didn't see epsilon.
No, right.
How did you achieve this?
Because the algorithm that I showed is how to produce R.
Ah, okay.
That produces R. You turn that algorithm into one with epsilon by, at this point, before you set k to k plus 1, before you repeat here, you set k to k plus 1, so now you have xk, which is the output of the previous step, and before you jump into this repeat, you check whether the proximity of xk is less than equal to epsilon, and if it is, then you don't go into the repeat. So that's how you code it. You just put an extra line in here to check on the proximity.
You put this line down or up?
This is it. This is the whole algorithm.
It's like repeat until the
No, there's no until. In this algorithm never stops. It doesn't give you an output. I mean, that was the observation. Yeah. This is an algorithm to produce an infinite sequence.
He produces
this algorithm produces the R. If you want to produce the output, you put in an extra line between 3 and 4 and say, instead of saying repeat, you say while PRXK is greater than or equal to epsilon, you get all this. That probably would be, from the computer science point of view, So replace the repeat, which goes infinitely. You put a 1 while PRXK is greater than equal to epsilon. That will do it.
The
Is that
question
clear?
is, how do you select epsilon? Because
well,
everything depends on epsilon.
In the examples I showed, we took, we just wanted to compare things with what people have been using. We used the method that people are currently using. They produced an output according to their stopping criteria, and we calculated the proximity of that output. And then we set that to be epsilon in the superiorized version. So for the sake of comparison with something existing, do your best with this. Then if we use for epsilon the proximity of your output, and we compare how well we do with the phi. No, if you're not comparing it, then that's always a problem when you have an iterative algorithm. Then you stop it, right? You have to have a stopping criterion, and how useful what you're doing will be depends on how good you are choosing your stopping criteria. If you stop too early, that may be a bad thing. But as in the case of the expectation maximization algorithm, if you stop too late, that's a bad thing, because there comes a point when you start putting the noise. So there's quite a bit of literature for expectation maximization as to when to stop it. And in particular, there was a paper published either earlier this year or late last year in IWCIA Transactions on Nuclear Science, which introduced an algorithm called EM stop, expectation maximization stop, which proposed a stopping criterion for expectation maximization in the nuclear medicine field.
Thank you.
Okay, thank you. Some more questions, remarks?
Yeah.
Is that like there should be some class of problems which can be superiorized? Is that somehow characterized? Which those algorithms where this improvement would really help?
No. I mean, right now, and this is what the heuristic says here, we don't have the general theorems in that sense that where this approach would definitely help. So in that sense, we are weaker than exact optimization, which is full of nicer mathematics. So we've been doing a great deal of work. We believe that this is very useful, and we've been doing a great deal of work of applying it in different fields. I indicated some of this. Another paper that appeared just a month or so ago in non-destructive testing, which I've written jointly with somebody in Siemens at Munich, on reconstructing turbine blades from X-ray data. And we could show that using superiorization, you got much more accurate images of the internal structure. So we are accumulating evidence of the usefulness of this by applying it in different fields and different criteria. And that's all I have to say. You see, the thing is, for example, the theorem 1 that I mentioned here, these are necessary conditions for strong perturbation resilience. But they are not these are sufficient conditions. These are sufficient conditions for strong perturbation resilience, but they're not necessary. An algorithm could be strong perturbation resilient without satisfying all these three. Early days, this idea has been around for such a long time. I don't know of any necessary and sufficient conditions. I only have sufficient conditions. Having necessary and sufficient conditions would allow me to say that this particular algorithm cannot be superiorized. I can never say that yet, because just because the algorithm violates theorem 1, it doesn't mean there isn't another algorithm by which it turns out to be this strong perturbation as again. But this whole field, I would say the very first paper on this topic, which you won't find the word superiorization in it, because the word came later, but the very first paper which discusses this appeared in 2007, so we're...
What would happen if you take a superiorized algorithm and do it one more time? Would it be possible? Or it's already not possible due to not satisfaction of some of those conditions? Well, if you have, when you have that algorithm, that it technically would be possible to put there already superiorized.
Oh, you mean it's quite superiorized?
Yes.
Yeah, I guess you could. I don't know. I haven't tried. Well, yeah, indeed. Especially if you have a multi-criterion optimization, you could take this and take one of the criteria. Then this is indeed just an algorithm. So you can take another criterion and plug into line 18 this algorithm with phi and optimize that for psi. Yeah, that's certainly possible. I haven't tried.
Okay, thank you very much. Are there some more questions or remarks? If not, let me thank again Professor Gabor for coming, and let me give him some small souvenirs to remind him he's visiting in Czech Republic at this.
I hope it's some Moravian wine.
Thank you very much.